Thanks to you all for coming, and thanks to the organizers, and of course, the staff who makes this event possible. My name is Alex Papandrew. I'm the program manager for clean energy at Mott Corporation in the United States. And I come to you to talk about our porous metal architectures for tomorrow's energy landscape. I think Jan gave us an excellent entry into this area of technical inquiry. And like Porous, Mott has been working in many different business areas for over 60 years. Of course, we're not Porous. We're a small company, employee-owned. Every one of our employees is an owner. And over the last 60 years, we've been working in diverse areas from oil and gas to aerospace to clean water to healthcare. We make things as large as a multi-story skidded water purification facility to a tiny implantable medical device that can dispense medication to someone's eye who's suffering from macular degeneration. So instead of getting a shot every week, they get one shot of an implantable device, and that lasts for 6 months. So Mott's been serving society for a long time. We put materials in spacecraft. We had a filter on the Opportunity rover that extended its life from 90 days to 15 years. We filtered out a lot of the dust that allowed that to happen. And now we've been moving into clean energy. And in clean energy, especially when we start to talk about hydrogen, one of the most important components in the entire clean energy space is what's called the porous transport layer. In a PEM water electrolyzer, the porous transport layer is a porous metallic component that is directly adjacent to the anode, which is the electrode that is responsible for oxidizing water, releasing oxygen, and transporting protons across the polymer exchange membrane, where they can later be turned into hydrogen, which is the value-add product. In the polymer water electrolyzer, the requirements for this component are so difficult to meet that only titanium is really sufficient to do that. Because in addition to the functions that the material has to do, delivering water to the anode, discharging the oxygen, collecting current from the anode, sinking heat, protecting the membrane, it has to be extraordinarily resistant to corrosion and maintain that resistance for 10 to 20 years, as well as maintaining extremely high electrical conductivity. So in many ways, titanium is special. And Mott has a special way of fabricating titanium to optimize it for these PEM water electrolysis systems. You can see on the lower right here some micrographs and some photographs of our PEM water electrolysis porous transport layers, and you can see that they're extremely regular. This is grade 2 titanium, exceedingly pure, basically the grade that's used for medical implants. So we've been making these for a long time. They've gone up into spacecraft. They've gone under the sea in submarines. But now, the world is changing, as we know, and there's a much more interest in green hydrogen. That's why we're all here. And if you look at the number of projects that have been announced, this is from the IEA database, you can see that in our titanium gigafactory in Farmington, Connecticut in the United States, we have enough capacity to be able to supply essentially the entire electrolysis industry with PTLs. And to some extent, we do that. But as green hydrogen gets uptake in the market, we expect there to be an explosion in the number of projects, especially in the PEM case. Alkaline water electrolysis has been around for a very long time, but PEM has a lot of advantages that companies, governments, national laboratories are seizing on, and we believe is going to lead to an incredibly large influx in investment and projects in the PEM space. So even though we see that in 2030, maybe we have 6 to 10 gigawatts of announced projects, I think we all have a feeling and a hope that it's going to be more than that. And Mott has the capability to, by 2030, to again meet that demand up to 15 gigawatts per year of PTL production capability. So as the industry grows, we're going to grow with it, and we're going to be there to supply our products for the PEM electrolysis stacks of the future. So how do the PEM electrolysis stacks of the future, how are they any different from the PEM electrolysis stacks of the past? I mean, certainly if you've got a good product, you can simply keep making that and keep selling it and raise the price as you go. But the economics of electrolysis are changing as the world changes. And at the core of that is the price of iridium. As many of you may know, iridium is irreplaceable in PEM electrolysis stacks, no matter what anybody else tells you. No other material is capable of lasting 10 years at the anode of a PEM electrolysis stack. And that's a problem because iridium pricing has gone wild in the last 8 years. If you look at this chart on the left there, that's the Johnson-Matthey just raw bullion chart for iridium. And you can see that in 2016, we were looking at maybe $500 per troy ounce of iridium. And for those of you who are not jewelers, a troy ounce is 31 grams. But correlated with COVID, perhaps, and some other wackiness in world events, we see around 2020, there's a huge jump in the price of iridium. Now we're looking at about $5,000 per troy ounce. So essentially a 10x in the price of iridium. That changes the economics of the electrolysis stack entirely. Because now you can see that whereas previously, pre-2016, I could put 2 milligrams of iridium per square centimeter of stack and still add less than a cent to the cost of the hydrogen I was trying to sell. Or to look at it another way, less than $10 per kilowatt of stack. Now, with 2024 pricing, if I want to put 2 milligrams per centimeter squared of iridium in my stack, I'm already looking at almost 4 cents per kilogram of hydrogen and more than $50 per kilowatt of stack. If we want to get down to $1 per kilogram of hydrogen, obviously paying 3 cents per kilogram just for the iridium in the stack, that's exclusive of everything else. That's obviously a non-starter. So what we are trying to do is develop a next generation of porous transport layers that are able to work effectively in the case of extremely low iridium loadings. But what you see in the literature, and I'm showing on the left here, this is a figure from Professor Gastiger's group in Germany. What you see typically in the literature is when you try to drop loadings below, say, 0.4 milligrams per centimeter squared, you see some extremely strange behavior in terms of the change of cell efficiency. Now, this stems from the fact that the anode of a water electrolysis cell at low loadings of, say, 0.2 milligrams per centimeter squared, it's a micron to 2 microns in thickness. So looking at one of our PTL products here, you can see that the gray is the metal, and there's black where there's no metal. So essentially, you have these huge gulfs that have to be bridged by the electronic and proton conductivity of the anode. And especially when the anode is very thin, that places a lot of stress on that thin layer. It has to absorb a lot of heat, and it has to take up a lot of activity. So we see that typically when you drop from 0.4 to 0.1, you see this categorical difference in the behavior of sintered PTLs, which is what Mott makes, and fiber PTLs, which are made by other companies in the world. When dropping from 0.4 to 0.1, the sintered PTL has a small change in the cell efficiency at 3 amps per centimeter squared, but the fiber PTL has an extremely large change in its efficiency, and that has to do with the geometric effect. Simply, there is more contact to the anode, which is the most precious thing you can have in a low-loaded electrolysis cell in the case of the sintered PTL. So we learned how to engineer the structures of our PTL to optimize the surface, because in a PEM water electrolyzer, that is where all the action happens. We know from seeing that picture from the Gastiger group that the anode is essentially two-dimensional. So really what matters is the planar interface between the PTL and the anode. So what I'm showing here are some light micrographs of our legacy and our next-gen PTL. And what looked like a very smooth, perfect surface in the case of those SEM micrographs a few slides ago now looks like the Grand Canyon. compared to our next-gen PTL, which is exceedingly smooth and perfect. We use smaller particles, the pores are smaller, the pore size distribution is tighter. And then, even at this 0.1 milligrams per centimeter squared, with our next-gen material, we're again able to reap even greater benefits from this next-gen approach. And this is entirely morphological. Everything else is the same in the cell. This is just by changing the surface structure of the PTL. And again, you can see that the IR-free curve shifts a little bit lower. And that's evidence that we've got some effects that go beyond just resistive effects of the contact of the anode to the PTL. We're reaping some kinetic benefits here as well. So that's what's really exciting for us. So we've started to actually study the fundamental functional relationship between porosity and performance when the loadings get low. And I think this is a fairly new learning that the US national labs and the academic groups in Europe are starting to get wise to. But the reason that it's new is because it's been obscured in the past. Because loadings in the past were 1, 2 milligrams per centimeter squared. You can still buy commercial CCMs at 3 milligrams per square centimeter. If you use 3 milligrams per square centimeter, you could put a chain link fence down as your PTL and the performance would still be fine, okay? What you see here is sort of evidence of that, and I'm being glib, but at 0.4 milligrams per centimeter squared, there's virtually no dependence of either the cell voltage or the high frequency resistance on porosity. But as soon as we drop down to that aggressive 0.1 milligram per centimeter squared loading, all of a sudden we see this very sharp correlation between loading, porosity, and performance. This is extremely interesting. What this tells us is that we should actually be striving to make the porosity of our PTLs lower to reap the benefits of ultra-low loaded CCMs. Now, obviously, if we go to too low of a porosity, what happens is that we'll start to restrict the transport of water to the anode and restrict the transport of oxygen away from the anode. So the cell voltage plot in that case would look like a V. And the high frequency resistance plot in that case would look sort of like a hockey stick. As we go in lower porosity, the ohmic resistance doesn't change, at least until we start drying out the membrane, right? So resistance and performance are correlated at this mid-range, again, simply because of a geometric effect of the PTL in contact with the anode. We want as much of that contact as possible. Water transport and oxygen transport are secondary. Water is 55 molar. Trust me, you will get enough. Okay? So this is a new finding, and we're talking with the national labs in the United States. With our new DOE grant, we're joining the H2NU consortium and starting to work on problems like this. But I think that the academic and national laboratory teams should take problems like this up and try to understand this at a fundamental level. Our next-gen sinters, like we talked about, have a fine, smooth, and more perfect surface. And you can again see this in optical micrographs of anodes that have been subjected to a simple short-term test. The anode itself starts out pretty flat, but after less than 24 hours of testing, again, you can see the strong embossing from our legacy PTL, where we see these big pits that are essentially the negative of the primary titanium particles in the legacy PTL. Those are incipient points of cracking or failure for an anode. In the case of the next-gen PTL, we qualitatively see much less damage. So this is a proxy for durability. And durability is where it's all at, because we want to amortize the cost of our capital over as long a time as possible to get the most bang for our buck. So with that, I'll say that Mott has the capacity to supply your clean energy product, no matter how big or how small. And we're finding a really strong correlation between PTL porosity and cell performance. And sintered porous metal is unique. It has unique properties, and advantages in preserving activity and durability under these leading edge conditions. So with that, I'd like to thank you. Please come and meet us at stand C136.